Hello everyone, I'm Sanghyeok from KAIST. This is the official presentation for EfficientViM, EfficientViM Mamba with hidden state mixer-based state-space duality, which is accepted in CVPR 2025. We first briefly review the concept of state-space models, which is the core operation in Mamba architectures. In state space models, given the input at each timestamp, it first updates the hidden state. Then it generates the output based on updated hidden state. Here, one difference between simple RNN and state space models is that all the projection parameters A, B, and C are dependent on each input. This is called selective mechanism in Mamba. To design the efficient global operation, SSM adopts hardware-aware implementation, which minimizes the memory input and output operation. It also adopts parallel association scan. Given the definition of SSM from previous slide, we can express the hidden state of each timestamp as follows. Once we list up the hidden states, we can see the notation BI, XI is repeated. So in SSM, it first calculates them in parallel manner and reuse the results once they need it. Also, you can see the A is cumulatively multiplicated, and this can be also parallelized through the parallel associative scan as follows. So Mamba is the combination of selective mechanism, hardware-aware implementation, and parallel scan. As a result, it efficiently captures the global dependency compared to RNN or transformers. In the vision domain, early works such as VIM and VMamba have been proposed. Since state space models inherently impose causal modeling, which is not ideal for vision tasks, these models apply SSMs across multiple scanning passes, for instance, forward and backward paths at a time. More recent works have eliminated the causality of SSM by proposing non-causal state space duality called NCSSD. NCSSD is defined as in here. Unlike the original SSM, the input xt is first mapped to the hidden state space via BT, and the global hidden state is the result of a weighted average of entire sequence using AT as the coefficient. So in NCSSD, it first generates the global hidden state and generates the output by adaptively projecting it with CT. Here, the important point is that the hidden state acts as a reduced latent array, which is typically much smaller than the number of input tokens. Based on this, we propose hidden state mixer-based state space duality called HSM-SSD in the following page. This figure illustrates the original NCSSD layer, which contains input projection and gated linear operation along with NCSSD. Based on this, we propose our HSM-SSD layer as in right figure. Given the layer input, we first map the input to the hidden state. After that, considering the hidden state as a reduced latent array, we apply the all projections including gating operation within the hidden state space. Lastly, by mapping the hidden state back to the output space, we conduct channel mixing operation within the hidden state space. Here, the total cost of original NCSSD is bigger of R&D plus LD squared, and the cost of HSM-SSD layer is R&D plus ND squared. Here, the first term R&D indicates the cost to map the input to hidden state space and back to output space. And the second term, LD squared and ND squared, is the cost to projection, the input and hidden state, respectively. Note that generally we adopt much lower n compared to the length of tokens L. This simple change largely increases the speed. Additionally, for more acceleration, we also break down the runtime of HSM-SSD layer. And we figure out that the runtime of a layer is largely determined by the memory-bound operation, which is not reflected in the flows. For instance, copy and reshape operations introduced by the multi-head design account for up to a quarter of the total runtime. So in EfficientViM, we adopt the simple single-head design. While this slightly increased the flows, we observe that the actual throughput improves by around 10%. This is the overall architecture of efficient VIM. In each efficient VIM block, we sequentially stack the HSM SSD layer and a feed-fault network along with stepwise convolution. And MSF indicate the multi-stage hidden state fusion. We use the hidden state of each stage and final output tokens as the input for MSF. Here, each input is pulled to obtain a global representation, then we compute the logit based on each global representation. Finally, combining these logits with their corresponding runnable weights, we generate the final output logit of the model. During training, this technique encourages auxiliary classification tasks for early layers, and also during inference, it enables to capture multi-scale representation. By combining all the components, the family of efficient VIM shows the best speed-accuracy trade-offs, especially compared to mobile-led and previous SOTAM method SHVIT. It brings 80 and 7% speed up along with slightly higher performance. Also compared to previous Vision Mamba's efficient VIM brings promising speed up. Overall, efficient VIM is extremely efficient architecture, outperforming all lightweight vision models and Mamba-based vision models. We further demonstrate the scalability of efficient VIM in high-resolution images. Thanks to the linear cost of HSM SSD layer, in the high-resolution scenarios, efficient VIM shows the much lower latency compared to other methods. And efficient VIM remains applicable in various downstream tasks like object detection, instance segmentation, and semantic segmentation. And it is also applicable with other edge devices like CPU and mobile platforms. This is the summary of efficient VIM. First, we propose a lightweight Mamba-based architecture called Efficient Vision Mamba. Second, as a core component of efficient VIM, we introduce HSM SSD, which controls the major overhead of SSD layer by adjusting the number of hidden states, interpreting it as a reduced latent array. Lastly, with a design that minimizes the memory-bound operations and incorporates the multi-stage hidden state fusion, efficient VIM achieves the state-of-the-art speed-accuracy trade-offs. This is the end of the presentation. Thanks for your attention.